patterns and ignore those small yet very important technical advancements, right? And then as a result, you can very easily conclude that all this is old ideas and nothing is new, right? So it's kind of like one. But I think the important thing is that both of those views are actually very biased, that we really need to take the view of both directions. So for example, I think it's important to always recognize the connections to old ideas or methods so that we can efficiently leverage our past experience when we did the same idea in the past and avoid making the same mistake, right? So that's very important. At the same time, I think we should also often remind ourselves to acknowledge those differences, even if those are maybe small technical differences, because maybe those small technical differences is what makes a big difference. Like what is the missing piece that pushes the field forward. So with this big picture, I think today my goal for this talk is try to talk a few of my past work and then kind of provide some sparse data points along this path, and also most important, put those lessons in context so that hopefully we can extrapolate forward with what we should do next, or what's the path forward. Okay, so first let's start with the question. Like actually, I think about a while back is why I want to work on deformable objects. I think when I just started my job in Columbia, I chose to work on deformable object manipulation because I think this task really forced us to remove the assumptions in our problem formulations for robotics, right? So because we're removing all the assumptions, maybe if we can conquer deformable object manipulation, it will provide us a path to manipulate anything in the world. So we all know that deformable object manipulation is very hard because objects deformable has very complex dynamics. They have near infinite degree of freedom and also under-actuated. So because of those differences, a lot of action space design actually is really well suited for deformable object manipulation, right? So for example, the typical pick-and-place action is actually very inefficient because each time that you pick up the class, you only affect a very small region of the class. So although it's kind of silly, like looking at the video now, but at the time when I just started, that is kind of the common practice for manipulating deformable objects. So as a result, oftentimes you will see the video play very long to make very small progress. So instead, I think we all know that when we are manipulating deformable objects, this is something that we actually do, right? We probably just use some kind of dynamic and fast motion in order to kind of control those out-of-contact surfaces. So right, in this particular example, the person is using the fling action to control the out-of-contact surfaces of this car. So with this observation, our first time on deformable manipulation is kind of have this lessons or this idea of let's use dynamic actions for deformable objects. And then that is lead to the very first paper that I published in this area. It's called fling bots. So the idea is actually very, very simple. It's just let's use fling actions for class unfolding. It's not even unfolding the class, it's just unfolding class. And then here is just a quick comparison of the system in action. With the fling action, with the dynamic action, you can actually quickly unfold the class just within 2 steps. But in comparison, if you only use polystatic pick and place, it's going to take the system a very long time to make very small progress. So that's exciting, but I think what's more exciting is that after FlingBot, we actually see many work actually incorporating dynamics action in their full system design. And here just a partial list of them, and even including the most recent demos from physical intelligence, their Paz0 demo. They actually, if you look carefully, a lot of those class manipulation tasks, they actually use this fling action. But I do need to point out that in order to achieve that kind of behavior, they actually use very different methods. They actually learn from demonstration, and that difference will come back to it. And then after I did the project FlingBot, the next question I asked myself is, can we make this dynamic manipulation more precise? Right. So for FlingBot, if you just care about unfolding a class, you actually don't really care about positions because you just want to increase the surface area. So in order to force myself to think about that question, we actually studied this problem of low conditions, dynamic manipulation. So here is 2 examples of those kind of tasks. One is if you are swinging a rope, you how to control your action so you can precisely hit the target goal. And the other task is kind of similar to FlingBot. You try to unfold the class, but you want to unfold it in a particular configuration, right? So in both cases, the goal configuration is defined by those key points, either on the tip of the rope or the corners of those claws. So when we are doing this project, I think the most important lessons I learned is that we actually don't need a very accurate dynamics model to learn an effective policy. And so I think this is actually quite interesting because when we are thinking about dynamic manipulation and deformable objects, the first thing coming to mind is that can we build a better dynamics model to model those objects? I think it's still very useful, but what we found is that if you formulate your problem properly or formulate your action properly, you actually don't need to have such a high requirement on a dynamics model. And sometimes inaccurate model is actually sufficient if you can perform action iteratively and know how to adjust your action based on visual feedback. And so, for example, this is what attempt that we're trying to build very accurate dynamics model for deformable objects. So we are using state-of-the-art simulators, and we're measuring error parameters of the rope, and we also calibrate the robot to execute the same action. But as you can see, there's still a big gap. Like the effect of this action is very different from the simulation and the real world. So if we just learn a full dynamics model in simulation and try to transfer it in real world, there's almost no hope that it will transfer. So instead, the idea is that let's learn a delta dynamics model, where the delta dynamics model only learns how to change the action, or like how the changes in action will result in a change of the effect. And that's hopefully, at least the direction of the changes is generalizable from simulation to real world. And we can use that to adjust the range. So here is the overview of the method. So basically, the delta dynamics model will take in the observation of your current action and also current rope trajectory, and you're taking a delta action. And then the output of the model is how the delta action will change or update the trajectories. Right? So it doesn't need to predict the trajectory from scratch. You only need to know how to change the existing observation. And the key here is that we're going to train this delta dynamics model in a very inaccurate physics simulator that I just showed you earlier. And then the big question now is that if you train this delta dynamics model, can you generalize to real world? And so we actually, in real world, we test quite extensively with many different ropes with very different dynamics models, with very different dynamics properties. Right? So for example, the second case is actually just a long piece of rope that's with very high air resistance. And then the third example is a ball whip that has non-uniform linear density. So both of those properties are just not captured in our simulator, therefore not captured in our training data. And the question is whether the delta dynamics model allows us to handle those kind of cases. Well, the short answer is yes. In here, I'm just showing you the final results when the policy actually converges on different ropes. So actually, each time the robot will actually iteratively adjust the action based on the delta dynamics, and then in the end, it's always able to achieve the target by this iterative process. And then this idea of using very inaccurate dynamics model or inaccurate simulator in general is actually very common in my prior works. So here I'm actually just showing you two of the examples. So the first example is we're trying to use aerodynamics, like blowing errors, to the class in order to unfold the class. And then the second example is trying to learn how to cut deformable objects like avocados. As you can see that for both scenarios, having a very accurate physics model, either for the aerodynamics or the mixed material object, is extremely hard. But what we show is that you can learn you can still use those inaccurate simulators to bootstrap your learning. And then in the real world, you can use your sensory feedback to adjust your action so that you can do the task very accurately. Right? So in the first case, we actually use visual feedback, and in the second case, we actually use force feedback in order to adjust the action. So if you want to know more about the details how to make this work, you can check out our old website. And then at the same time, I think in parallel, another lessons we learned through all the projects I talked about earlier is that a well-designed action primitive can drastically simplify your learning. So for example, in many of the projects I just showed you, actually rely on a very good, well-designed primitives. So for example, for the fling block project, we already designed the primitive of how to fling. So the model actually doesn't need to know the fling action from scratch. The only thing you can learn is where to grasp the class in order to execute the fling action. Right. So, and similarly for the rope task, we also designed the swing primitives. So the nice thing about designing action primitive is that you can map your very complex action sequence into just a few learnable parameters. Like for example, where to grasp the class. So as a result, you can drastically improve the learning efficiency and then just make your model to focus on learning the most critical parameters. So that's actually very useful if you in robotics, because we oftentimes don't have a lot of training data to train on. But at the same time, we actually, after we do several projects by using action primitive, we slowly realize there's also limitations. So for example, in order to design a very effective action primitive, you really require the engineer to have a very deep understanding about the task and also the robots, right? So how we actually formulate this fleeing primitive with two arms, there's many different ways you can formulate it, but we actually need to think very carefully about how to design it. So there's a lot of engineering effort that's needed. And also at the same time, you need to like manually tune your parameters in order to make the primitive effective. And I think most important limitation is that all those action primitives is actually not general enough to really represent all possible robot actions, especially the robot actions that requires high rate reactive behaviors. Because within the action primitive, you actually don't adjust your action. But if you want the robot to be very reactive to the dynamic world, that will not work. So therefore, the first lesson to learn is that the action primitive can also limit the system capability. So that is actually lead to our like more recent work, and then we actually quite changed recently. I think many of our own projects we changed the kind of approach for approaching a new robot task quite differently. So instead of using well-designed action primitive for learning, we're kind of moving towards the paradigm that we just try to directly learn those complex skills from data, and in particular human demonstration. And this is actually a big switch after we have done this diffusion policy. So many of you may be already very familiar with diffusion policy, but here is just a high-level overall pipeline if you're using diffusion policy or any other learning from demonstration pipeline to design to make your robot to do the task. Right? So oftentimes the first step is quite simple. First, you can think about the task that you want your robot to work on, and then you collect some training data with teleoperation or some other methods, as long as you can collect the robot data to do the task. And then you can train your diffusion policy or whatever policy formulation you like overnight. And the second day, you have the robot that's able to do the task, the same task. So if you look at this very simple pipeline, the most important thing that I want to highlight here is that we no longer need to design action primitives. So instead, we offload the difficulty of just collecting the robot training data. And if you can tell your robot to do the task, you pretty much can train the policy that allows your robot. So I think for diffusion policy, what makes it really special is this iterative learning process, and which we found out is actually has a lot of benefits. And one of them is that it allows you to model very complex multi-model distributions. So another, I guess, the second thing that we learned in this project and also later project is that action multimodality is not a corner case. It actually happens very, very often. Right? Even if you are not like demonstrating the task differently, imagine you are demonstrating the same task with the same action, but one time faster, one time slower. You actually have action multimodality. So in some sense, if you have a method that's able to model action multimodality better, overall it will give you a better performance. So that's why I think it's such an important concept to understand and also an important challenge to address. So here is just a quick like overview for a lot of tasks that we are able to do with just diffusion policy. And I think at the time, what's really kind of convinced me that this is the right way to go is the demo on the top right, which is this cut flipping task. So if you look at this video, it's actually uncut video that the robot is just keep flipping the task, I remember 20 times without failure. And if you see this whole process, the robot actually is constantly switching its behaviors like grasping, pushing, reorienting, and sometimes if you miss the grasp, it will actually recover the mistake itself. Right? So at the time, I was realized that it's going to be really, really hard for me to code out a primitive or a set of primitives to do this task. So that is the example that convinced me that it's actually a better way to kind of learn this complex behavior directly. Okay, so at this point, maybe some of you are already like thinking about this question. Is either learning from demonstration one of this idea that we see it many, many times in the past. Actually, if you actually take any robot learning course, the first few lectures is probably about learning from demonstration and why it doesn't work. Right? So actually here I'm just list out a few reasons why it won't work. Like the first is difficulty of model action, complex action distributions, and then also the extensive data collection process. It requires a human in the loop, And the last one is that oftentimes if you learn from behavioral cloning method, your policy often has lack of generalization capability. You cannot generalize to new scenarios or new environments. So all those criticisms or concerns are actually very valid. They have very good reason to worry about why it won't work. And then, but here I want to highlight what is the difference? What is the small step? Well, I guess the small step is that we change the policy representation so that it can capture the action distribution better. And I also have to say, this is probably the only difference that we made, because the remaining challenge is still there, right? When we are releasing diffusion policy, we did realize that it's still very expensive to collect global demonstration data. And also the policy I just showed you does not generalize. That it actually needs to only deploy in the same environment that you collect the data on. For the cup flipping task, it cannot flip another task. So it cannot generalize. Those limitations still there. So how can we improve that, right? So that leads to kind of the last lessons that we learned in this process, is that collecting high quality demonstration data with dynamic and diverse actions is actually very hard. And so that's actually forced us to think about new ways of collecting global demonstration data that is not like using, for example, back then we used space mouse to collect global demonstration. So that's kind of motivated us to work on this a project called Universal Manipulation Interface, where the focus is to think about how we can design the data collection interface so that we can kind of gather more natural human demonstration, and then so that we can have more complex skills as well as better generalization capabilities in the future. So the overall idea for UMI or Universal Manipulation Interface is that instead of trying to do in the lab teleoperation or in the wild, or directly learning from the in the wild human video, we want to choose something in the middle that's basically designing a handheld paper that people can hold, and then also use that to collect the diverse training data. So at the same time, this device is that allows us to transfer the learned skill to robots. So simultaneously minimizing the embodiment gap, but still remain intuitive for the human. So that is the idea. And then, but if you at the time actually we thought about this is actually not a new idea also. And in this time, the old advisor is actually me, because I myself did this idea a few years ago. So I actually have this paper called Grasping in the Wild, published I think 4 years before UMI project. So the idea is that we can actually add a sensor to like a grabber tool, and then you can collect human demonstration data with this kind of portable device. So I did it a few years ago, but what the lessons I kind of learned at that time is that although theoretically like the user can hold this paper to demonstrate a lot of tasks, the data actually is not always transferable. Right? In reality, a lot of data you collected with a paper like this cannot transfer to an actual local policy that works. So as a result, a lot of those devices actually constrain to very simple actions. For example, in the paper that I published, I only demonstrate on grasping actions and deposit static pick up this. It's not able to do very complex tasks like dynamic manipulation or even manual manipulation. So what's the difference? So I think the high-level summary of the difference is that we have a lot of better engineering design choices in both the hardware and software design, in order to make the system actually works for very complex manipulation tasks. And I guess maybe another key difference is that the student Chengshu and Zhenjia, they're just much better engineers than me, and they're able to make the system work a lot better. So I'm gonna give you just a high-level overview of some of those important design decisions. I'm not able to cover all of them, but here is a few that I think make a difference. And so the first of all is that the choice of camera. Back then, what I used is the Intel RealSense that actually has very low resolution and has very limited fluid. So as a result, when you're manipulating an object close up, you don't see too much context. And we also have trouble tracking the camera pose very accurately. Especially when you have fast motion. Actually, Intel RealSense will have motion blur, so as a result, it's very hard to track. But what Zhenjia and Cheng did is that they changed the camera to a visual lens. Therefore, it can provide you much wider visual context for the system to infer what should be the right action to do under a particular conditions. And then they also, because you have a wider field of view, the visual tracking is also more reliable, and it has more features to track on. And then they also add a small side mirror on the side of the camera to give you the implicit stereo information without the requirement of having a depth camera. So as a result, we don't need to carry, for example, a laptop with us like when we are using Intel RealSense. And another, I think, a smart decision, this is actually inherent from the TRI gripper design, is to use the soft gripper instead of like a rigid gripper to collect data. So this soft gripper provides a lot of compliance when you're interacting with objects. And also, it provides a little bit of implicit force information through the deformation of gripper. So even if you are not using UMI to collect data, I think this gripper design is still very useful, and you can kind of borrow it to your robot as well. And then on the software side, they actually also had made a few important changes that to make the system work. So for example, they did a very good job on trying to match the latencies, because when you collect data, there's almost no latency between your visual observation and action. But when you deploy the policy on the robots, there's a lot of latencies from the sensory input to action execution and policy inference. So you actually need to be careful about how to handle the latencies, both in the input and output side. And then, of course, another change is that they changed it to diffusion policy. That helps a lot as well. And I think another small but very important change they made is the action representation. So in diffusion policy, we actually predict action trajectory already, but the action trajectory oftentimes we represent in the global coordinate frame. But in this particular paper, we actually represent the action trajectory in a relative coordinate frame. That is always relative to the first action in the whole trajectory. So by representing your action this way has a few benefits. One is that you no longer require global calibrations of your camera. Yes, everything is relative to the current camera frame. So you don't need to actually calibrate what's the current camera and with respect to the robot. As you can imagine, it's very convenient for UMI's kind of setup because we don't really have global frame for UMI. And another small kind of important benefit that we found actually later is that by using wrist mount camera with relative action trajectory, you actually also get sample efficiencies in learning, because this representation is actually invariant to the input observation. So as a result, even if you are not using UMI and if you're using diffusion policy, this is actually a very valuable change you can make in your code base to change your action trajectory to be relative. And I think that will actually give you 1 or 2 points of performance boost at least. Okay, so those are some design decisions they made, and I think made a difference. And as a result, we can actually show quite impressive demo with UMI. Like for example, this bimanual cross-folding, dishwashing, and also tossing, right? So this tossing task is in particular the one that's difficult, and you need to handle the latencies very well in order to make it work. And then here is just a kind of highlight for the cross-folding task, which is something that I want to do back then, but very difficult with tally operation. But now, with this kind of pair of UMI gripper, you can easily collect training data for this task. One small thing is that when you have UMI on both hands, you cannot stop the UMI by using your hands. So you actually need to use voice control to stop the gripper for recording. Okay, and then for generalization, because I think the idea is that because UMI is so portable, you can carry it into different environments, you actually can collect a very diverse training data. So if you're able to do that, your policy automatically will just generalize better in different environments. So we really try to stress test on this generalization by driving our robots around the campus and evaluating their performance. So to quickly summarize on the last part of this talk, is that the difference that we made is actually a set of small but very important hardware and policy interface design, and then therefore it enables effective transfer from the human demonstration to robot policies. Right? Although the idea has been shown many times, but I think all the engineering details is quite important. So with the new UMI design, we actually can make the data collection more intuitive and portable, and therefore reduce the cost of data collection. And then also at the same time, we can do in-the-wild data collection, therefore, which at least show a possible way for the BC policy to generalize, but just increasing the diversity of training data. And then here you have it. This is all the 5 lessons I learned on deformable object manipulation. Like for example, dynamic action is very useful for deformable objects, and we don't need a very accurate dynamics model to do very accurate like dynamic diffusion tasks. And then well-designed action primitive can simplify your learning, but at the same time, they can also limit your system capability. And then finally, I think it's still open challenge for the last point is collecting high-quality demonstrations with diverse actions are difficult, and we need to work more on that. And I think most importantly, I want you to remember this mental picture when we're thinking about all the past work and also thinking about what's the path forward. Thank you. Yeah, sure.
Okay, great. I love this talk. Thank you so much. I really appreciate how that alone is very interesting the way you're thinking about that. I totally relate, right? And I also really there's so many things I want to ask you about. I'm gonna limit myself to just so I really like your choice of the UV reference parallel draw. And I'm curious if you can say a little more about that because obviously we just came from the trade shows filled with hands, dexterous hands. And I'm with you on the parallel draw. I'm a big fan. But I'm curious, what's your motivation for that? And do you think that is in a way all you need, maybe for many manipulations?
Yeah, so actually we do have follow-up work on Lumi that is making it multi-finger. So it's called Dex Lumi. It's hard to stop my student work on that. It's just a so hot topic right now. I think it makes sense to like thinking about what's the next, like thinking about dexterous hand. I think that definitely will eventually give us better performance and capability. However, if you ask me today, I still really value the simplicities of parallel draw gripper. I think many people didn't realize that how powerful you can or how many tasks you can do with just two parallel draw gripper. I think with one it's very hard to do a lot of tasks, but if you have two of them, you also has all the contact points that you can actually do like in-hand orientation, change the object pose. So it's actually very, very powerful. So I remember Matt Mason has this very old talk called simple gripper for complex tasks. I still believe that. And I think in engineering, there's a lot of times it's doing this trade-offs between simplicity and capability. And I think parallel draw gripper still have a pretty good like trade-off at this point. Yeah. But of course, we should still develop dexterous hands and make it more capable.
So, thank you, Shuran. Yeah, it was a very nice talk and a very nice wrap up of everything you've done. And so, considering that we are in a deformable object manipulation workshop, so my question is like, as we saw in the debate yesterday, like data approaches provide you like a general approach where you solve everything. So we don't need to care about how we represent clothes, like it's basically the same than rigid objects. My question is it like, do you require more data? How much more data you require for the deformable objects, or it's just the same?
Yeah, I definitely feel like they're not exactly the same. And actually, deformable object, just as I said earlier, it's naturally a more complex task because of the high dimension of the possible state space. So as a result, it probably requires a lot more data. Right? So I think if I just do a p-complex task, I can get away with 10 demonstrations. But for deformable object, like for the class, at least you need hundreds or even thousands if you want to see generalization. So I think it intrinsically has a complexity that is actually more complex than rigid objects. And also, I think it also comes with a lot of other challenges. For example, how to simulate deformable objects is very different from simulating rigid objects. So if we really look at deformable object manipulation, I think there is definitely a lot more things to study than rigid. So however, if you just mostly focus on deformable object, then that's probably fine, right? Because most of your method could potentially generalize to rigid object as well. Yeah.
So, but then you need to test not only in different objects, but also like in one single object to get a lot more data. Like,
yes, yeah.
And is the performance like in the past that you showed with the unit with that folding, is the performance the same as with the other tasks?
I don't remember the exact numbers, but I think the performance, the data definitely will require more, and also depends on the horizon. Like when we do the folding, the horizon is longer, so naturally it requires more data. So I think the performance probably maybe is similar, but like naturally we need more data for it.
Because like when you are like moving and then you have these constraints that the arms cannot like move apart too much because otherwise you lose the cloth. Like,
yeah.
Like, do you see future in trying to put this kind of structure, or is it well like?
Yeah, that's a very good question. Should we put in those structures? So in the Flinkball paper that I showed very early, we actually have that structure. So right, when we like predicting this primitive, we actually make sure that it is not too far, not too close, so that don't collide or don't stretch the claws. In the later work, we don't have that structure, and we do from time to time see that's actually just invalid, that it actually cannot be executed. So I think it's a like very interesting and debatable question on how much structure we want to add. And right now, I don't have a very good answer. I can tell you that if we have less structure and just do behavior cloning, that is actually more engineering friendly. Like if you don't understand too much about the problem, you can get systems to work to a degree. But if you understand the problem really, really well, and you're a very good engineer, and you can put in the right structure to the problem, you can probably achieve better performance. So that's kind of like the trade-off.
I So that siempre va a bien.
That's pretty